Hello children, welcome to the physics class. This is our fourth presentation. In this, we will be seeing about electrostatic potential energy and potential, electrostatic potential due to a point charge, and then electrostatic potential due to a dipole, equipotential surface, and the first derivation is electrostatic potential energy and potential. Now for this, you consider the diagram. You consider a positive charge Q which is kept at the origin and which produces an electric field E around it. You know always if you have a charge, an electric field will be created around it. Now a positive charge Q dash is brought from the point R to the point P against the repulsive force. Okay. The repulsive force is acting between Q and Q dash. So work has to be done to overcome this repulsion. So this work is stored as your potential energy. Okay. Now the test charge Q dash is brought from R to P. As we said, it is brought from the point R to P with a constant velocity, which means the external force used to bring the test charge Q dash from R to P must be equal and opposite to the Coulomb force. Okay. Therefore, we write F external is equal to minus F Coulomb. Now, since this Coulomb force is conservative in nature, work done is independent of the path and it depends only on the initial and the final points or the positions of the test charge. Now, if the potential energy associated with Q dash at P is represented as UP and that at R is represented as UR, then the difference in the two potential is defined as the work done to bring a test charge Q dash from R to P. Therefore, we write the equation as UP minus UR is equal to W, which is equal to del U. Now, del U is nothing but integral of F external dr vector. Now you know F external is equal to minus F Coulomb, which is equal to Q dash E, because F is equal to Q into E. So we write it as minus Q dash into E. Substitute the value within the integral. So Q dash becomes constant, so it comes out. So integral of minus E dash dr within the limits P to R. Therefore, del U by Q dash, this is nothing but the quantity. This is referred to as the electric potential difference between P and R, and it is denoted as Vp minus Vr. Okay. And in other words, the electric potential difference is defined as the work done by an external force to bring unit positive charge from point R to point P. Therefore, we write it as Vp minus Vr is equal to del V, which is equal to integral of minus Er E vector dr. Okay. Thus, the electric potential difference can be written as del U. Okay. Therefore, the electric potential at a point is equal to the work done by an external force by the external force to bring a unit positive charge with constant velocity from infinity to the point P in the region of the external field. Now the important points that has to be noted: electric potential at a point is equal to the work done by an external force, as I told you, to bring a unit positive charge with constant velocity from infinity to the point P in the region of the external electric field. Electric potential P depends on the point P. On the point P depends only on the source charge, and the unit of electric potential is joule per coulomb. Sorry, it is joule per coulomb, and the practical unit is volt, named after Alexander Volta, who invented electric battery. Then the potential difference between 2 points is expressed in terms of voltage. The next one is electrostatic potential at a point due to a point charge. Again, let us consider a positive charge Q, which is kept at the origin, and let P be a point at a distance R from the charge Q. Now the electric potential at the point P is given as V is equal to, we already know the equation, integral of minus E vector dot dr vector. Okay. Now we know from our previous equation that the electric field is going to be represented as 1 by 4 pi epsilon naught Q by R square. Just substitute that value over there. So instead of E vector, you write it as 1 by 4 pi epsilon naught Q by R square. Since 1 by 4 pi epsilon naught is a constant, we can just bring it outside, and we know that dr vector is nothing but dr into unit vector r vector, and using the identity r cap into r cap is equal to 1, we get your equation as v is equal to minus 1 by 4 pi epsilon naught integral of r integral of q by r squared r cap vector into dr r cap vector. So that gets cancelled, it is equal to 1. So I get my equation as 1 by 4 pi epsilon naught with a minus sign integral of r to infinity q by r squared into dr. Or if you integrate, you bring q outside, and if you integrate 1 by r squared, you get it as minus 1 by r. So minus and minus gets cancelled. So my value of potential V is going to be equal to 1 by 4 pi epsilon naught Q by R. Now if the source charge Q is positive, V will be greater than 0, and if Q is negative, then V is negative, and it is equal to minus 1 by 4 pi epsilon naught Q by R. So the points to be noted over here is, if the source charge Q is positive, V is greater than 0. If Q is negative, then V is negative, or it is equal to V is equal to minus 1 by 4 pi epsilon naught Q by R. The potential due to the positive charge decreases as distance increases. Note the point, potential due to the positive charge decreases as distance increases. For negative charges, potential increases as distance increases, and at infinity, V is equal to 0. Next you have electric potential. In this, it is compared with your gravitational potential energy. That is, in the case of gravitational force, mass moves from a point of higher gravitational potential to the point of lower gravitational potential. Similarly, a positive charge moves from a point of higher electrostatic potential energy to a lower electrostatic potential energy. However, a negative charge moves from lower electrostatic potential to a higher electrostatic potential, which is described in the diagram. Now we are going to discuss about electric potential due to a dipole. This is a very important question, children. Now you already know what is a dipole: two equal and opposite charges separated by a small distance. So the two equal and opposite charges are minus q and plus q, which are placed at A and B, separated by a distance of 2a. So the midpoint is O. So the distance between AO is equal to A. Similarly, the distance between OB is equal to A. That is how you get your 2A. And let us consider a point P, which is the distance of R from the midpoint. And the angle subtended along POB is equal to theta, and the angle subtended along AOP is equal to 180 minus theta, because the total angle should be 180. So if this is theta, the other angle should be 180 minus theta. And the distance between the positive charge and the point P is represented as R1, and the negative charge and the point P is represented as R2, and the distance between the midpoint and the point P is equal to R. Now, in order to calculate the potential at P due to the dipole, we'll have to calculate the potential at P due to the positive charge separately, and then due to the negative charge separately, and then we'll have to add these two terms. Now the potential at P due to the positive charge is given as V1, which is equal to K by Q by R1. Now K is equal to 1 by 4 pi epsilon naught, which is a constant. Similarly, the potential at P due to minus Q is represented as V2, which is equal to minus K Q by R2. So the total potential will be the addition of these two. So I get my equation as K into Q, because I brought my Q outside as a common term, into 1 by R1 minus 1 by R2. And I repeat, K is equal to 1 by 4 pi epsilon naught. Now, to find out the value of R1 and R2 in terms of R, we need to do a certain calculation which have been represented. Now calculation for 1 by r1 and similarly for 1 by r2 I have given over here. Now we are going to use the cosine law for the triangle BOP. In the triangle BOP, the angle subtended is equal to theta. Now if I substitute my cosine law, it says as, the equation goes as r1 squared is equal to r squared plus a squared minus 2ra cos theta. Now in that equation, I am just going to divide, I am going to bring r squared outside and divide by r squared. So I get my equation as 1 plus a squared by r squared minus 2a by r cos theta, because r squared and r will get cancelled. So I get it as 2a by r cos theta. Now since we can neglect a squared by r squared term since it is very small. So I can neglect that term. So my equation becomes as r1 squared is equal to r squared into 1 minus 2a by r cos theta. Now I need r1, okay, and similarly actually I need 1 by r1, so I'm going to take r1. So I'm bringing r1, if I take the root of it, so I get it as r into 1 minus 2a by r cos theta to the power of half. Root can be represented as to the power of half. Reciprocal, 1 by r1 is equal to 1 by r into 1 minus 2a by r cos theta to the power of minus half. Now I am implementing binomial theorem here. When I implement binomial theorem, I get my equation as 1 by r1 is equal to 1 by r into 1 plus a by r cos theta. Now to calculate 1 by r squared, it is just going to be the angle only will change. That is, instead of cos theta, I am going to write it as cos 180 minus theta. 180 minus theta means will be equal to minus theta minus cos theta. So the equation will become as r2 squared is equal to r squared plus a squared plus 2ra cos theta. Same steps are involved, and I get my equation as 1 by r squared is equal to 1 by r into 1 minus a by r cos theta. Now from the previous equation, we have just substituted the value of 1 by r1 and 1 by r2. So I get my equation as v is equal to kq 1 by r into 1 plus a by r cos theta minus 1 by r into 1 minus a by r cos theta. Now 1 by r can be brought outside, and rearranging the terms, whichever is getting cancelled, we can cancel, and you get your final equation as v is equal to k into 2aq cos theta r squared by r squared. Now you know 2a into q is equal to p, therefore I have substituted v is equal to k p cos theta by r squared, since p is equal to q into 2a. Now you know k is equal to 1 by 4 pi epsilon naught, so your equation for v, the potential, will be equal to 1 by 4 pi epsilon naught p cos theta by r squared. Now this can be represented, since it is cos theta, you can represent in terms of dot product as p vector dot r unit vector by r cos theta by r squared. So my equation is v is equal to 1 by 4 pi epsilon naught p vector dot r cap by r squared. Now you have certain special cases in this. When theta is equal to 0, that is, if the point P lies on the axial line of the dipole on the side of plus q due to the positive charge, which lies on the side of the positive charge, then theta will be equal to 0. Then from the equation, that is 1 by 4 pi epsilon naught p cos theta by r squared, if theta is equal to 0, cos 0 will be equal to 1. Therefore, v is equal to 1 by 4 pi epsilon naught p by r squared. If theta is equal to 180 degrees, that means if the point P lies on the axial line of the dipole on the side of minus q, then you know that cos 180 is equal to minus 1. Therefore, v will be equal to 1 by 4 pi epsilon naught p by r squared with a minus sign. Now, if theta is equal to 90 degrees, that is, if the point P lies on the equatorial line of the dipole, then when theta is 90 means cos 90 is equal to 0. Therefore, the potential V will be equal to 0. The important points to be noted: the potential due to an electric dipole falls as 1 by r squared. Next, the potential due to the dipole is not spherically symmetric because potential depends on the angle between P and the position vector r of the point. dipole potential is axially symmetric. Now if you see the diagram, you can understand what is the meaning of the dipole potential is axially symmetric. Now if the position vector r vector is rotated about p vector, keeping theta fixed, okay, the angle subtended is going to be fixed and you're going to rotate it, then all points in the cone at the same distance r will have the same potential. Okay, that is the blue curve will have the same potential. Next we come to equipotential surface. As the name implies, an equipotential surface is the surface on which all the points are at the same potential. So in the diagram we have the charge in the center and you have the points A, B, C, D. All of them are at the same distance, so all of them will be at the will have the same potential. So they are termed as equipotential surface. The other diagram which shows you the equipotential surface. Okay. Next we have the relation between E and V. Now you know E is your electric field and V is the potential. Now if you're going to consider a positive charge Q which is kept at the origin, now in order to move the unit positive charge by a small distance dx in the electric field E, work has to be done, and this work is written as dW, which is equal to minus EDX, where the negative sign implies that the work is done against the electric field. Now the work done is equal to the electric potential difference. Therefore we write it as dW is equal to dV. Okay, or dV is equal to minus EDX. Just substitute the value, you get it as dV is equal to minus EDX. Now just to rearrange it, you get it as E is equal to minus dV by dx. The electric field is the negative gradient of the electric potential, or in general you can write this electric field as this. Okay, I think I will stop with this. Please go through the slides again and again, children. Thank you.